Alright, so welcome back. This is section 1.1, part 2. We are still working on a little bit of review. We're going to talk about symmetry right now. What does it mean to say a graph has symmetry? There are three types of symmetry we often concern ourselves with. We have x-axis symmetry, y-axis symmetry, and origin symmetry. This first example here would represent y-axis symmetry. Y-axis symmetry is where if you were to draw a line down the y-axis, the left and right hand sides are perfect reflections of each other, that every point x, y is reflected over to negative x, y. Okay? So it is a reflection across the y-axis. Right? Now similarly, x-axis symmetry, you're doing the same thing, but you're doing with respect to the x-axis. Now you're a flip up-down. Okay? So it is a reflection across the x-axis. So points that are up here reflected down to there, points that are down there reflected back up to there. Now the hard one to see, or the hardest one to see, I guess I should say, is origin symmetry. Because it's a reflection across the origin. It is a reflection across the line y equals negative x, because it's a reflection across actually two lines at the same time. It is a reflection across the origin. And so another different way to think about it is to reflect across the x and then across the y, or similarly you could reflect across the y and then across the x, but you end up down there. Now, for each of these though, there's a relationship that exists. A point xy gets reflected over to a point negative x, y. Right? Now this is a good moment to talk about something that shows up in mathematics. Is that a negative number? The answer is I don't know, because I don't know what x is to know what the opposite of x is. All I know is that negative x is the opposite of x. So if x started out as a positive number, then yes, negative x is a negative number. But if x started out as a negative number, then negative x would be a positive number. Same thing is going to happen here. If I have a point xy, it's going to get reflected to the point x opposite of y, negative y, but I don't know whether that's a negative y value or not. And then down here, right? There are tests for symmetries. To test symmetry of a graph with respect to the y-axis, you replace x with negative x, and if after you work out the mathematics of it and simplify it, you're back to the original equation. If it yields an equivalent equation, then you have y-axis symmetry, because x and negative x should give you the same y value, because x and negative x should give you the same y value. The test for symmetry with respect to the x-axis is to do something similar, but to replace y's with negative y's and see if you get an equivalent expression, because y and negative y should both give you the same x value. That is, y and negative y should give you the same x value. The harder one to see is the symmetry with respect to the origin, because it asks you to replace both x and y with the opposite, negative x and negative y, and see if you get the equivalent expression. Because in the origin one, xy should be the same as negative x, negative y, or should give you that reflection, and so it should give you the same values in the equation. Okay. We don't do a lot of symmetry stuff, but it can be useful from time to time. A more important skill, though, is to be able to find a point of intersection of two, or potentially more graphs. A point of intersection is where it is a solution point that satisfies both equations. That's the algebra behind it. The geometry behind it is it's a point of actual intersection. The geometric definition is where the two curves intersect. Right? The way that we find points of intersection is we find our points of intersection by solving the equation simultaneously. All right. So what I would like to do is I would like to find all points of intersection of this and this. Now, before we even get started, I'm realizing that this is a parabola and this is a line. So depending on how this goes, let's see, I think that's a parabola opening down and a line. It could have potentially a couple intersection points, right? Or maybe it could just have one intersection point, or maybe it could miss and have no intersection points. So before I even get started, I'm looking at this saying, this could have 0, 1, or 2 possible intersections. Okay, so now that I know how many I'm looking for, I'm going to go ahead and find these things. Now, the way I solve this simultaneously is... All right, so I'm going to set up a system of equations and solve. I have x squared minus y equals 3. I have x minus y equals 1. Let's see, since one of these is linear and one of these is quadratic, I'm going to use a technique called substitution, where I'm going to solve one of the equations for one of the variables and substitute into the other equation. I'm going to choose to solve the second equation for y, and when I solve that second equation for y, I get the y is equal to x minus 1. And then I'm going to take that and substitute it into the first equation. Well, that arrow doesn't look good. I'll take this. Whoa, whoa, whoa. I still don't want that arrow. Well, what happened there? I'll take this and substitute it into the first equation, which then gives me x squared minus x minus 1, because that's our y, is equal to 3. So I have x squared minus x plus 1 is equal to 3. X squared minus x minus 2 is equal to 0. So notice that I'm setting this thing equal to 0, so I can use that zero product principle technique again. That's going to give me x minus 2 times x plus 1 is equal to 0. Zero product principle then, I get that x minus 2 is equal to 0, or x plus 1 is equal to 0, which means I get that x is equal to 2, or x is equal to negative 1. So we found the values for x, but what were we trying to do here? Our job was to find points of intersection. A point contains an x and a y value. So the fact we have x's doesn't mean anything. Now I have to take these x values, put them back into my substitution statement, and find the corresponding y value to get my points of intersection. So I'll do x is 2 first. If x is 2, then y is equal to 2 minus 1, or x minus 1, so y would be equal to 1. Or if x is negative 1, then y is equal to negative 1 minus 1, which would be a negative 2. So the final thing that I'll do is I'll wrap it up and make it look pretty and say that my solution is the intersection points are, let's see, 2, 1, and negative 1, negative 2. Now this is a by hand technique, but I also could have solved this graphically. I could have gone over here to Desmos, right? And I could have said, okay, let's graph these two things. What was the first one again? We're looking at x squared minus y equals 3. So x squared and the second one was x minus y equals 1. And there's our intersection points. All right, same answers we got, just a different technique. All right, that brings us to the end of section 1.1, so I'm going to end the video here. The next video will be section 1.2. Have a good one.